All right, good morning. Um, I'm not a caffeine person. I don't drink coffee, but I've only had 2 hours of sleep yesterday night. So I'm just having coffee, so don't mind that. Good morning. My name is Arun Gupta. I work for Amazon Web Services. When I submitted this talk, at that point, I was not a AWS employee. But so it turned out that, hey, this is actually talking about AWS stack, because I think that's a cool stack. So essentially, in this talk, I'll talk about how do you deploy your microservices using AWS S3, which is an unlikely candidate. Why would I use S3 for deploying my microservice? We'll talk about that. API Gateway, AWS Lambda, which is Amazon Web Services serverless stack, and Couchbase. That's the database that I used at that point of time, because that's where I used to work. Like anybody and everybody, I got a Twitter handle, so here it is. I'm a Docker captain. I've been talking about Docker for a couple of years now. I've written a book on Docker for Java developers. I'm also a Java champion, so talk about Java very actively, and then a bunch of other things. I like to run. I'm very proud of finishing my first ultra marathon a couple of weeks ago, so I'm enjoying that part of it, and I'm always looking for new topics, new technologies to learn. Let's jump straight into it. Now, this is sort of the standard canonical definition of microservice. Now, this is given by Martin Fowler, and essentially, if you think about this, it talks about how microservices are taking a big application, refactoring it into a smaller applications, which are each running in its own process. So what I'm going to do is I'm going to go through this definition, highlight the key parts of it, and then we will revisit this definition towards the end of the presentation, which will hopefully give you a little bit more clarity and context. So each application in the microservice-based architecture is running in its own process. They talk to each other using lightweight API, typically using HTTP REST API. Each application is independently deployable, upgradable, replaceable. You talk through the contract. You don't care about what is the underlying implementation. There is very minimal amount of centralized management. There is no scaling. I mean, if you need to scale, you just call that many concurrent connections. You don't say, okay, now scale my application. That's the important part of it. It truly allows you to use the right language for the right microservice. So it's truly polyglot in that sense. And similarly, the data storage technologies. It's just because you have signed an end user license agreement with Oracle or some other company, you're not stuck to that data store technology. If you want to use a NoSQL database or some other sort of database like a Redis or Elastic Cache, sure, you should be able to do that. So it truly allows you to use that full gamut of tool as opposed to having a golden hammer that, hey, everything is going to go through Oracle database. So if you look at a microservice architecture, now if you look at an application which has a bunch of microservices, if you think about this at a very high level, essentially it's a bunch of web pages with some JavaScript in there. Each of that page is somewhere invoking a REST backend. So you have a bunch of REST endpoints over there. Those REST endpoints are then backed up by a code. There is a code that is getting executed, could be Java code or something else. And then finally, it has a database at the backend where it says, okay, you know what, these are sort of your main steps that you need to do in order to build that microservice-based application. How are these applications composed? That is completely dependent upon your application. So if we look at it from a different perspective, it is also the MVC architecture. So you got your model on the right side, which is where your code is defining where do you write to the database and what database do you write to. Then you got your controller, which is your REST endpoint, and which is what is being fed by your view, which is your JavaScript pages. A slightly different perspective of the same as well is, if you look at it, your JavaScript and HTML is over there. Your REST API is basically get, put, post, delete. That's what you manipulate with. Then you have your code could be sitting as a Lambda function. We'll talk about that. And then finally, your database could be whatever database you care about. Now, where does S3 fit in? S3 has the ability to host your static websites, and we'll talk about that a little bit later. But your REST API could be very well hosted by API Gateway, as opposed to mixing your logic with your business logic itself. Lambda is where your business logic sits, and so you're truly separating your REST API as part of API Gateway and business logic only in the Lambda functions. And then Couchbase is your database where you are storing the state. So let's talk about serverless computing. What is serverless computing? one of the first things you need to realize is, serverless computing is probably not the right term, first of all, because people say serverless computing means there are no servers in the backend. Yes, there are servers in the backend. It's just that you are not responsible for managing them or scaling them or monitoring them or patching them or upgrading them. Now, typically, if you have server-based computing, what are the challenges? I don't know what is the performance that I need for my application today. Maybe I know it today, but I don't know how it's going to go in the future. So I don't know how much budget to allocate. Should I over allocate, depending upon my resources? At what point do I scale my servers up and down? Yes, I can write the monitoring code, and based upon that, I can do the scaling up and down. But again, that's something that I need to be responsible for. Let's go a step up. What operating system should I use? Debian, Ubuntu, CentOS, or do I get more driven by where my company has signed the end user license agreement? What operating system settings should be there? I need to tune it for my right database connection pooling. If a new patch comes up, I am responsible for patching. How do I access the control to the servers? And then lastly, deploy new code to the server. Now, these are known challenges. We have known these challenges for a while, and there are good workarounds, or at least workarounds for each of these. But these are known challenges typically when you own the database, when you own the servers, and when you are responsible for upgrading, patching, managing the servers. So let's take a look at it. How does virtual machines, and I'm not going to go into what containers are. I presume you know containers. But so I'll compare and contrast. How does your virtual machine, containers, and serverless really differ from each other, knowing what we know about server-based computing? So in terms of virtual machine, your unit of scale, as we say, is a virtual machine. So you want to scale your pool of virtual machine, you add one more virtual machine to it. In terms of containers, typically your container is packaged as an application itself, so you can scale your application. And in terms of serverless, or a better term for that is function as a service, so to say, your unit of scale is a function, because your application consists of multiple functions, and you can scale that one function by itself. In terms of abstraction, if you look at virtual machine, you don't care what is the hardware it's running on. Because if in terms of AWS, you say, hey, give me 4-core, 16 gig, and that's what you get. It doesn't matter whether the underlying layer is Intel or AMD or something else. You say, this is what I want, and this is what you get. Similarly, in terms of containers, you say, run a Docker container. You don't care whether it's running on an Ubuntu or a Debian or on what operating system. So container is your level of abstraction. And in terms of serverless or fast, as so to say, the abstraction is your language runtime. You say, hey, I want to run a Java function. I want to run a Node function. Or I want to run a JavaScript function. And when I'm running Java, I want to run on Java 8. So that is your abstraction. You don't care about what is the underlying operating system or hardware for that sake. So there's a different level of abstraction depending upon what are you using. In terms of packaging, there is AMI packaging or AMI. That is what you do for EC2, for example. In terms of containers, there is a Docker file or a container file, which is where you bring your image and you run your container over there. And in terms of serverless, you're down to the code. That here is the code, here's the Java function, go package it up and deploy it. And I'll show you several examples of that. What do you configure in all of these different means? In terms of virtual machine, you are responsible for the machine, storage, networking, operating system, all of that. So if you want to scale your machines, you want to create a EC2 cluster, then you will install on each EC2 instance, then you will network them, then you will create an auto-scaling group, and all of those, you are responsible for that. On containers, you run the servers, you configure the applications, you are responsible for scaling. So you need to write some sort of a monitoring code. Now come to serverless, you write the function, and you run when it's needed, and the scaling happens behind the scene for you. We'll talk about that. In terms of execution, again, if you look at it, in virtual machines, you can do multi-threaded, multitask. In containers, it's multi-threaded, but single task happens because containers do only one thing. And in terms of serverless, it's inherently a lot more secure because it's single-threaded, single task. Talk about their lifetime. How long do they run? And in terms of virtual machines, typically hours to months. If you're running containers, they're typically minutes to days. And if you're running serverless or functions, essentially, they run from microseconds to seconds. just to kind of compare and contrast a little bit. And then in terms of cost, of course, virtual machine standard is per VM per hour. Containers typically you run on a virtual machine or on a server somewhere. That cost is also per VM per hour. But in serverless, it kind of takes it to the next level where it says, oh, cost is per memory per second per request. So if you invoke a function, depending upon if it executes for like 15 seconds and using 2 GB of memory, I'm going to only charge you for that. And last but not the least, in terms of Amazon, what are the stack that is being offered, or rather AWS? There is, of course, EC2. And then in containers, you can have Docker, Kubernetes, ECS, DCOS, a whole variety of orchestration systems. And then in terms of serverless, there is AWS Lambda. Just kind of a good comparison of the three programming paradigms, so to say. Now, people typically often confuse that, hey, serverless means PaaS. The key part that you want to understand is if your PaaS can start efficiently in 20 milliseconds and then run for half a second and then can do that again and again and again, yes, you can call it as a FaaS. So that's an important part to understand. PaaS is typically meant for that, okay, there is a platform as a service available to you. Maybe it's JBoss, maybe it's Tomcat, and my server is a long-running server, and it's all warmed up, all performance optimizations done, and I'm going to invoke it, and that's it. And it's probably a long-running process as opposed to a quick process. So with that, what is AWS Lambda? So AWS Lambda is essentially it allows you to focus on your business logic. You write your application logic in the language of your choice. So today there are 4 different languages that are supported. So Java, Node, Python, and C#. Those are the 4 languages that are supported today. You write your business logic, and then you deploy your code to AWS Lambda. There is 0 administration required. That means you don't care, you don't need to know what are the EC2 instances running behind the scene. It's highly available because once you fire up the code runs, and then it exits out of it. It's purely stateless. And if you want to run 500 concurrent connections, you do 500 concurrent execution. All the scaling, all the administration happens for you behind the scene by AWS infrastructure. We talked about the metering part of it a little bit, but essentially you're charged for every 100 milliseconds of execute time. There is no storage cost. So because essentially what you do is you package up your Java function as a zip file, you upload that zip file into AWS Lambda. There is no storage cost. The only time it charges you is when the function is being executed, and depending upon how much memory is being taken and how much is execute time. And we'll talk about that a little bit later. But that's far better than saying, okay, per VM, per hour, because let's say if my function is being executed only for like 30 seconds, then rest of the 59-minute, 30 seconds is just sitting idle over there. And then the continuous scaling part of it is, again, because you don't care about the administration, the management, the monitoring aspect of it, if you want to invoke that function 100 times concurrently, you can do that. All of that is done automatically for you behind the scene. So how does it work? Well, you write your business logic literally as a simple Java function. So you take an application, you break it down into multiple functions, and you take that function and you upload to AWS Lambda. Then that Lambda function could be triggered by multiple triggers, so to say. So one of the triggers could be by using a REST API. The other trigger could be I'm calling it from a mobile application. The other trigger could be during test and dev, I'm calling it from a Maven project itself. So lots of ways by which these Lambda functions could be triggered. Now, once the Lambda function is triggered, AWS runs the Lambda function. Whatever it takes, it goes through the function. We'll talk about what the function looks like. And it uses only the compute resources that are required. So let's say when you say, I need to run this function in 2 gigabytes of memory, it takes only 2 gigabytes of memory. It accordingly allocates your CPU and your networking resources. So you only care about the memory part of it. Everything else is automatically allocated to you. And then you just pay for the time consumed. And by the way, the payment also is very cool because the first 1 million calls per month are free. So whether you are a paid user or a free user for AWS, sign up for AWS account. First 1 million calls to AWS Lambda are free per month. Well, this is what the pricing part of it is. So the 1 million free requests per month, and essentially what that gives you is 400,000 gigabyte seconds of compute time per month. CPU and network, as we talked about, are allocated appropriately. But essentially, if you look at this here, depending upon what are you allocating, you could run it. You can say, okay, when I'm running my method, I need only 128 megabytes of memory because it's a Python-based function, and it's a very simple function. Or I need a half a gig of memory, and then I'm going to allocate because I'm running Java 8, so I need a little bit more memory. So if you're allocating about half a gig of memory, which is at the bottom of the table, then what you're getting is about 800 free tier seconds per month. So you can run for 800,000 seconds per month, and that again resets every month. So if you're building a simple hello world application or a little bit more complex application, you get a lot of free time that way, so get to play with it. So what are the typical use cases? So this is a very classical use case for AWS Lambda. Essentially what happens is, you take a photograph, you upload the photograph into an S3 bucket. Now, the photograph is sitting over there, and because a Lambda function can be triggered by an object update or upload into S3 bucket, as soon as you upload into S3 bucket, the Lambda function is triggered, and all it does is, it takes that image and it generates different resolutions for different screen factors. And this is a very classical example that is used by Seattle Times and how they use Lambda functions. So anytime anybody uploads an image, it just automatically creates, because you know that desktop or cell phone or laptops or tablets, they're different resolutions, so it just creates that image automatically behind the scene for you. Another classical example, an online order is placed for you, for example. That order, once you place the order, that detail of that order goes into DynamoDB database, which is again a NoSQL database managed service by AWS. Now, a Lambda function can be triggered by a row being added to DynamoDB database, and you trigger the Lambda function. That Lambda function then runs the data transformation code and loads the results into the Redshift database, which is the data warehousing solution by AWS. And then you can generate analytics from that generated data. So as soon as your data order is placed, you're generating the full analytics of it by the virtue of using a Lambda function. A more classical example is, your front-end code is sitting in S3. That's sort of the model we will use later today as well. So your front-end code, which is all index HTML, JavaScript, all that code is sitting in S3 bucket. The user clicks on a web page. Then as soon as they click on the web page, that goes to API Gateway, which is where your REST APIs are configured. That REST API then triggers a Lambda function, which then talks to DynamoDB database to fetch the information from you. I mean, I'm using DynamoDB, but it could be any database that you care about, essentially. So let's take a look at it. What are the key components of my AWS Lambda function, essentially? Each Lambda function, first of all, needs to implement, I'm using a Java version of it here, but essentially, my Lambda function needs to implement this request handler interface. That comes as part of the AWS SDK libraries. And in that, there is a request and a response. So this defines this is a Java runtime, essentially what you need for it. The request is the data that is passed to the function. When you're calling the function in, you can pass different data. So in my case, for example, I'm using simple JSON payload. So I pass that JSON payload as part of my function, and that is accessible to in my function body. And in this case, if you look at it, in the line I'm saying string.format, rec.firstname, and rec.lastname, essentially the JSON parameters that I'm passing from my function, they're automatically available to me, bounded to my Pojo class, essentially, which is the request class here. And request is my Pojo, essentially. I define what request looks like. And then finally, I have a response, and response is again my own Pojo, and I define it how it looks like. From the AWS Lambda perspective, all you have is a request handler, and which says request is inbound, response is outbound, and the Java language runtime takes care of serializing it for you. And then the context is the second parameter, which gives you a little bit more detail about the runtime, the Lambda runtime itself, which says, okay, what is the unique request number and other context information around the Lambda runtime. So let me show you my very first Java plus Lambda function here. Let me increase my font size. So here is my hello world that implements request handler. As I was saying, the request handler comes from the standard Amazon SDK. So this is Amazon AWS library here. And if I look at my request and my response here, if I look at request is just my simple POJO with first name, last name in there. And then if I look at my response, that's again just a simple POJO as well. So the code is pretty simple, and this is all my functional logic is, essentially. Now, this is a very trivial hello world. Literally, it's a hello world as such. But if I were to package this together, now this is a Maven project, and in here, all I'm doing is I'm including AWS Lambda Java core library. So when I create my shaded jar here, which is sort of a fat jar with all the libraries included in there, then this Lambda Java core is included as part of it. Okay, and that's all I need. And I just need to create a fat jar here. And once I create the fat jar, then I will take that fat jar, upload it into the Lambda console, and then I say, go ahead, trigger this function. Okay. So we talked about how we need the AWS Lambda Java core library over there. Now, in order to create my Lambda function, I could go to the Lambda, AWS console and upload the function from there, where I'm actually pointing to the zip file or the jar file, which is the sort of the fat jar, or I can use the AWS CLI as well. In this case, all I'm saying is create the function. I'm giving function a name. I need to define a resource name also. So I'm giving that name and essentially the role in which the function is going to run. Because if my function has to talk to DynamoDB database, then it needs to have that role, the IAM role that AWS requires, in which it has the capability to talk to DynamoDB database. Then I'm giving it the zip file essentially, and then the zip file is essentially my fat jar that was created. Then I'm saying the description and runtime. All I need to say is Java 8. That's all I say. And then it automatically provisions behind the scene what is the Java 8 runtime. I give it a region, time, and memory. Remember, we talk about the half a gig or 1 gig of memory. So in this case, I'm saying 1 gig of memory, and I just publish the function. And then invoking the function is, again, very simple. I'm saying AWS Lambda invoke, function name, region, and this is the payload, essentially. So this is my custom payload, and here I'm saying first name and last name. These are my JSON parameters. Those JSON values are actually bound to my POJO, and that's how they're accessible to me in the code. So very straightforward. And hello world.out is where my response is written. So very simple hello world Lambda function. Essentially, if you were to go into the Lambda console, this is how it would look like. And here I have, of course, a few more functions. So you can see, for example, I have a couple of functions. In the runtime column, it shows there are a couple of functions with Java 8, couple with Node, and one with Python. So in that sense, AWS provides a rich variety of languages, at least to begin with. So let's talk a little bit about Couchbase. Well, Couchbase is a NoSQL document database. It's an open source NoSQL document database. It provides a lot of capabilities. You can, of course, store all of your JSON documents into Couchbase itself as is. It has the full querying capabilities. I think that's one of the unique features of Couchbase particularly, because it allows you to query your NoSQL documents or JSON documents using SQL syntax. So it has a full SQL-like querying capability called as NQL, and that allows you to run SQL queries on your NoSQL documents. So that is pretty cool. It has about 9 or 10 different kinds of indexes that allows you to use a primary index or a secondary index or a global secondary index, which makes the data access that much more efficient. It also has the capability for doing cross data center replication. So you can say I'm running one in the East Coast and one on the West Coast, and I want to set up cross data center replication between the two databases. That capability is there as well. It also has a simple version by which you can say, I want to run a Couchbase Lite on my mobile device, and then have that Couchbase Lite be automatically synchronized with a backend server, which is running somewhere in my data center. And then that Couchbase Lite, by the way, can operate in an offline mode. So if you lose internet connectivity, it will continue to work because your database is on your mobile device. And when the connectivity comes back online, then it'll connect back and synchronize with the backend server. So that capability is pretty cool, actually. And then over past few months, they've also added the capability for full text search and analytics ability as well. So let's see, my next example is, now I've written a simple Java function, which is hello world, but now I want to add some state to it. And state is in the sense that I should be able to talk to the behind the scene Couchbase database, okay? So let's take a look at that. So if I look at this here now, I have hello Couchbase Lambda. Once again, I have a request and the request and the response here you can see is a string type. So if I look at request here, so this is request, is just a simple POJO. There's nothing in there. I'm not really too much worried about what's coming in. Essentially, I'm getting all of my information from the context. And essentially, the way I wrote this application is, when I built my very first Couchbase plus Lambda connection, the Lambda function particularly was triggered by an AWS IoT button. And so what was happening was I had a bunch of IoT buttons on my desk. I would press an IoT button, that would trigger my Lambda function. And then as part of the context, I don't care about the payload this time, I care about the context, because in the context is telling me what is my AWS IoT button ID, what is my request ID, what is the time it is being invoked, and essentially I'm taking that context information and storing into my Couchbase instance. So here, for example, you can see I'm saying, okay, what is the time the request was invoked? Then from the context, I'm getting the request ID, and I'm setting the timestamp, and I'm storing that data into the database. And as you can see, handle request is one method here. I mean, that's the only method that you need to have. But in order to make a connection to the database, you need to take care of establishing a connection and then tiering a connection as well within that function itself. Oftentimes, I've seen people using sort of a database connection pooling library somewhere in between, where the Lambda function will go fetch a database connection from the pool, will use that connection, write it to the database, and then release the connection back to the pool just to be more efficient. I mean, in this case, all I'm doing is I'm establishing the connection every time, but that could add to the cost otherwise. So in addition to AWS Lambda Java core, I'm also including the Couchbase client library also in here as well. So that gets included as part of it, and everything else stays the same pretty much. Okay. One thing that will have to change though is, well, I mean, we have our Maven dependencies, we create the function, we invoke the function, but the key thing that we will have to include is now when I'm uploading my function, as part of that function now I can specify an environment variable, which says, where is it that the Couchbase database is running? So essentially I'm specifying a variable here called as Couchbase host, and I'm giving it an EC2 instance. Now if I go back here, in here I'm just reading the system.get.env Couchbase host. So once I'm reading the Couchbase host variable, and that's how I'm able to find out, okay, where the Couchbase host is running. All right, and so this is the example I was talking about. And this was a fun experiment that I did in our cafeteria, essentially. We had a red and a green button over there in the cafeteria. So people who will walk into the cafeteria, they have the ability to press either of the button. and that was sort of an instant feedback on the food. Very nerdy way of getting feedback on the food, but essentially you press a red or a green button, that's an IoT button, that goes and gives feedback, that triggers a Lambda function that goes and talks to a Couchbase, that stores the data, whether you like the food, you didn't like the food, and then you have a nice dashboard, a simple JavaScript dashboard front-ending it. So as opposed to this fancy box over here, we built it a little bit in a nerdy way. All right, so let's see the purpose of AWS API Gateway, and then we will start assembling our things together. So what is AWS API Gateway? AWS API Gateway allows you to create, publish, maintain, monitor, and secure your RESTful APIs. Now, if you are building applications using, say, Spring or Java EE, then you will put the annotation in the code itself. And anytime you want to alter how this APIs need to look like or how the parameters need to look like, you will have to change the code, repackage, recompile, all of that. And then there are other issues with it. So for example, you can't have metrics on how much API is being invoked. You can't start tying those APIs to a particular role or LDAP realm. At least that is not pretty straightforward here. So AWS API Gateway or any API Gateway product in that sense gives you the ability where it decouples, saying, you know what, this is your business logic, define the REST API and all of the security, authentication, authorization, metrics, metering, all of that as part of the API Gateway, and then bound it to the behind-the-scene business logic. And that way, they both can evolve independently. Another capability that is in the API Gateway is how you can manage multiple stages and versions. So you can say, this is my test version of the API, this is my dev version of the API, this is my staging version of the API, and then you can also have all the backwards compatibility aspect of it as well. So essentially, literally have your API designers and the function implementation guys completely separate or decouple if you need to. It is also integrated with CloudWatch, so you can see exactly which API is being invoked, how much time, and in case you want to start charging your customers for the billing purpose of it. In API Gateway, you only pay for the calls made to APIs and the data that is getting transferred out as part of that API. So what more things you can do? You can start setting throttling rules. So for example, you can say that when somebody is calling the put API, I don't want to have more than 200 puts in a second. So you can start avoiding your denial of service. Or if somebody is doing a get API, I don't want to have more than 1,000 gets per second. So you can start setting those throttling rules very easily as part of the API Gateway. We talked a little bit about the authorization and access control, how this can be very well integrated with AWS IAM or even AWS Cognito. Cognito is a solution by AWS, which is a service as well, which enables a social login. So if you want to do social login with your mobile application or a web application, that's a good service to look at. And the ability is that with API Gateway, once you have defined your APIs, it easily says, hey, generate my test client kit, so to say. So it generates SDKs for you, JavaScript, iOS, and Android. So you define your APIs, your code is implemented in Lambda, and now you have your JavaScript client automatically ready for you to go. So how does the flow look like in this case? I could have mobile applications, websites, or web services, whatever I want on the left side. They can invoke any REST API, essentially, that is defined as part of the API Gateway, of course, coming as part of the internet. So the APIs are accessible over the internet over here. So they make a call to the API Gateway. Now, in the API Gateway, you can also enable API Gateway cache. So if the responses are gets and they are not timed out, then you can start serving it from the gateway cache itself, in which case nothing needs to happen on the back end. Of course, if things need to happen, then you can invoke either a Lambda function, or you can invoke some business logic running on EC2 instance, or you can invoke any other publicly accessible endpoint. So all of that combination is possible. And of course, all of this is integrated with the CloudWatch monitoring. So that's an important aspect to understand too. So what did I do? Essentially, in my case, I wanted to build a simple microservice where I want to have the ability to do a CRUDing of a book database in Couchbase, and that's all I wanted to do. So here what I'm showing you is essentially the AWS console snapshot for the API gateway. So if you look at this here, on the top left, it says Amazon API Gateway. Then it talks about the APIs. Then it says, oh, this is my API. The book is the API. Then it talks about the resources. And in the resource, essentially, I got my two methods. So I have got get and post method, which are shown on the right side here, essentially. So get and the post methods are over there. And on the left side, which is the standard AWS console, you can start defining your models, your authorizers, all of your details, your usage plans, all of the details around API gateway can be specified using the AWS console itself. But the key part from our side is I have a /books resource that is accessible using get and post HTTP methods. So how does my essentially my microservice in that sense look like? So from a broader architecture perspective, I have a client, the client that talks to the API gateway, which can then invoke get or post method on the /books resource. And the get and the post could be two separate Lambda functions, which are then talking to Couchbase running on EC2. So that's sort of a simple architecture that I used for my simple microservice here. Now, what is your typical development workflow? Well, the typical workflow is you create your Lambda function, you upload the Lambda function, and you test it. That's your first step, of course. Then once you have done the Lambda function, then you will create your REST API using API Gateway. Then you will say, my Lambda function needs to be triggered by this REST API. And then you will invoke the REST API. So now every time you invoke the REST API, it will trigger the Lambda function, and you will get the result back. You test and debug, and then you keep doing it until you see that this is actually working. So let me take you to the next step. I'm sort of a lazy programmer in that sense, and I don't want to write too much code when I'm doing my work. I want the infrastructure to provide me the code or simplify things for me. So if I were to do this flow here, I have to write a lot of pieces by myself. Maven plugins or POM XMLs, and then upload, and then test it again, and then deploy it again. That's where AWS Server Application Model comes in. So serverless application model is a standard application model for serverless application. This is a specification that is being created on GitHub by AWS. Essentially, it extends CloudFormation templates. So CloudFormation template is nothing but it's a way by which you can create a set of AWS resources in a predefined way, and it just extends that. And so essentially, it adds new resource types over there. First is a serverless function. Then it says serverless API, and then it says serverless simple table. So API is the REST API, which triggers a serverless function. And similarly, simple table is a DynamoDB table or any updates to the DynamoDB table, which will trigger my Lambda function here. So there are new event source types, as I was talking about, S3 API and schedule. And then there are property types as well, like environment and event source, where the event is coming from. So here is sort of my template.yaml file for SAM, or Serverless Application Model. And let me walk you through this. So line 1, of course, it gives the template format version, which goes back to the original CloudFormation template version. And here it says, I'm going to apply a transform to this CloudFormation template, which is the version shown on line 2. Then on line 4 onwards, I'm defining what are my resources here, essentially. So I'm saying I'm just defining a simple resource by the name microservice getAll. And this is a serverless function, which is defined on line 6. In that function, I got certain properties. The property being the handler name. Handler is the function that is, because if you're building a Lambda function, there is only one entry point to the Lambda function, which is that handler function that we saw earlier. So it's finding the handler function, then you're saying the runtime. And if you're using SAM, it requires you to upload your zip file to a S3 bucket. So I'm now giving a pointer to my S3 bucket, essentially where my code is living. Then I put some other values like timeout, memory size. And then in this case, I'm also giving my Couchbase host as an environment variable, saying that, okay, this is where my Couchbase host is living. This one, SAM, so essentially, my flow would be Maven package that will generate my jar file. And then I will say, you know what, AWS CloudFormation, deploy this template, and I'm done. Because now my jar file is generated, my jar file is uploaded to S3 using a Maven plugin, and I'll show you how I do that. And then I just invoke this template. That's it. To make it fun, I can also add events, which says that, oh, by the way, I have my REST API created using API Gateway, which can be done using AWS CLI. And once I've done that, on line 41 through 46, I'm saying, oh, by the way, when you call this REST API /books with the get method, call this Lambda function. So all of that is very nicely tied up together using this serverless application model. So let me show you an example of that here. So here is my S3 upload Maven plugin. This is a standard plugin that I pulled from Maven Central. But with this allows me to really upload my jar file that I create using Maven package. And then I'm already tying this to the install phase. So essentially, I just need to say Maven install. That Maven install will create my fat jar. It'll upload the fat jar to S3. So that's step number 1. Step number 2 is I need to do one time, which is basically creating my API Gateway APIs. And once I've done that, then I can take the SAM, which is available to me here. So here is my sam.yaml, and I'm in the process of moving the Couchbase part of it to a DynamoDB database. I was just kind of trying to experiment with that, how that works. Pretty much very similar. So everything kind of stays as is as I'm migrating the code. All I need to change is just the DynamoDB variable. That, okay, now instead of Couchbase, my database that is being used is DynamoDB. And then in here, so in this case, for example, what I want to highlight is, here is my book get all function, if you look at this part of it. In this case, there is no trigger. All I'm saying is, here is a function, and this function needs to be invoked explicitly using AWS Lambda invoke AWS CLI. And now here, I have book all gateway method, where I'm saying, yeah, this is the handler function, but this function can be invoked when I really have a REST API that I need to trigger. So this function can be invoked with a REST API. So you can have like a variety of Lambda functions, one which can be invoked with CLI, test it that way, and then you can have your REST API and say, now I'm going to trigger it with the REST API. So you can have different levels of testing built into it. All right, so let's take a look at the last piece of our microservice where we were talking about S3. So what is S3? Well, Amazon S3 is I'm not going to get into the details part of it, but essentially think of it as an infinitesimally big bucket where you can store whatever data or object you want to store over there. It is very simple. It's just simple a key value pair. So key could be whatever your S3 bucket name is, and then in there you can store as much data as you want to store over there. It's 11 nines of durability essentially. So once the data is stored over there, it's pretty much there. It gives you the scalability part of it. Whether you want to store gigabytes of data or exabytes of data, you can retrieve anytime. It has all that multi-region replication capability. You can set up your access control on it, the type of access that you want for a particular object, whether you want read or write, and integrate with your IAM roles. All of that can be done very easily. So a little bit of AWS S3 concepts, if I were to explain it. In your AWS account, you have buckets. A bucket could have an object. The object has a metadata and a data. And in metadata, you have a key and a version. And then, of course, your data is there. So what really uniquely defines your object? Well, bucket and the key and the version. So that's uniquely identifies your data, basically. Okay. And so if I am storing lots of objects over there, that's how I can uniquely identify it. Now, here is my AWS S3 console, essentially. And the key part that I want to highlight over here is, yes, you have support for versioning, logging, cross-region replication, all of that. But the key part that you want to look at is on the top right, where it says static website hosting. On S3, I can upload a bunch of pages, and I can say, serve it as a simple website. So it just runs a web server for you behind the scene. And then you can use the S3 CDN network to use it as a simple web page. So you just enable, use this bucket to host a website. I can define my main entry page and an error document page. And then my microservice deployment architecture becomes like this. So now I have a client. The client can talk to CloudFront, which is Amazon CDN network, which then talks to Route 53, which is where my DNS domain is being set up. And then that DNS domain could go to microservice.arungupta.me, which is sort of my domain, or it could go to www.microservice.arungupta.me, which is redirected to the original one. And that's where my static S3 pages are living. So that's where I can host my static pages. That's where they're pointed to. Additionally, or optionally, my client could directly invoke the REST API, which then goes to the REST API Gateway, and where my REST APIs are hosted, so get, put, post, delete, where each of the function is then mapped to a Lambda function, which is then talking to a Couchbase database sitting in EC2. And in addition, what we can also do is the S3 API, where my HTML pages and JavaScript are living, they could directly invoke the REST API, for example. So you can really have very fancy combinations of how you want to build or deploy your service here. So let's go back to our original definition of microservice that we talked about. We talked about that how microservice is just a bunch of small services, each running in its own process. Now, thinking about Lambda functions, that actually makes sense because each Lambda function is a microservice for me. That's sort of my business logic. They are independently deployable. Yes, each Lambda function can be updated and upgraded at any point of time. They talk to each other using REST API, because that's sort of what my REST API Gateway or AWS API Gateway is providing. The microservice by themselves do not require any centralized management because it's a function as a service. So behind the scene, AWS is managing the entire infrastructure for you. There is support for different programming languages. So Node, Python, Java, and C# today. More languages coming in the future. And it is completely independent of the data storage technologies that you're using from your function. Essentially, you can connect to a MongoDB instance or a Couchbase or a DynamoDB database or a RDS or Aurora or Oracle. We don't care really. You build that logic as part of your Lambda function. So all the slides and the code that I talked about are available on my GitHub repo. So github.com/arun-gupta/serverless. So feel free to use them in any way. All the slides are available and the code is available. And that's where I continue to evolve and add more samples from my side of it. And I think that's about a wrap, if we have about a minute or two for questions. The Lambda functions? Now, that is, yes, I will. So what is the startup time when you, for any function, when you do invoke it for the very first time? You need to think about it that every invocation of a function is a new invocation of a function. There is no warm-up, essentially, that happens for a Lambda function. So you need to account into the fact that, okay, if it's using JVM, then the JVM will kickstart, and then it will invoke the function. And then when you do the second invocation, there is no guarantee. It purely depends upon the implementation of the backend that it may keep the function warm, but it's very likely that it may spin up into a different instance depending upon how many concurrent invocations are happening. And if you're doing a Python function, then there is no warm-up. You just fire it up and interpret it. So it really depends upon the language that you're using. I would say consider your each invocation of the function as of its own invocation and incorporate that warm-up time in there. I've seen some folks where they send a ping to the function every few seconds to keep the JVM alive. And that's sort of an anti-pattern, I would say, because then you're sort of killing the spirit of the entire stateless part of it.
Agree, but if it takes a few seconds to spin up for the first time, then you have if you're using a JVM,
True. True. No, absolutely. Well, I think that's true with any technology in that sense. The question being, if it takes a few seconds for the JVM to spin up, then you're restricting your choices. That's true with any technology in that sense. I wouldn't call serverless as a golden hammer. Because I have serverless, I'm going to take my big monolith and put it into a serverless and wait for a few seconds. So I think that we need to be a little bit careful about adapting serverless in that sense. Anybody has any other question?
Let's suppose that serverless becomes successful, and then I have many different lambdas on AWS. How do you organize them?
Yeah, so far the question is, if I have many AWS Lambda functions that are running for me, how do I really organize them? So far, the functions that I've played with, they are very small in number, and they're a lot easier to manage in that sense. But typically what I've seen is, for example, I was talking to somebody last week, and what they did is, their use case was, they get like a 40-minute long video, and what they need to do is, they need to convert that video from one format to another format. So the typical use case that I've seen is where the video comes in, they run the same, they take that video, 40-minute video, break it into chunks of 1-minute video, and they run the same Lambda function on that 1-minute chunk to kind of parallelize the execution part of it. So as opposed to having 100 Lambda functions, they have a one Lambda function running 100 times, parallelize the execution, and then they put the result back into there. But I agree, that would be like a genuine problem. If you have hundreds of Lambda functions, how do you organize them? And that's something I'll give a thought. No, the way I organize my Lambda function is typically my one Lambda function is in one jar. So as opposed to bundling multiple Lambda functions in a jar and then setting different handlers. I want that Lambda function to be fully independent by itself.
Yeah, that's what I saw, but then if you have hundreds of them, it becomes not super manageable in the user interface. Hence my question.
Right. Let's talk about that. I would like to understand more a little bit.
I hate to interrupt you, but in order to maintain the schedule, we need to stop here.
Yeah.
Maybe you'll be around for questions.
I'll be around for the rest of the day pretty much.
Yes. Thank
cool.
You.
Thank you.